Welcome. Today, we're diving into the world of edge computing networks. Edge computing brings computation closer to data sources, enabling faster processing and reduced latency. It's a transformative approach to handling data in an increasingly connected world. So, what exactly is edge computing? It's a distributed computing paradigm that brings computation and data storage closer to the location where it is needed. This improves response times and saves bandwidth. Edge computing reduces latency by processing data locally. It minimizes bandwidth usage to the cloud and enhances data privacy and security. The graphic illustrates the difference between traditional cloud computing and edge computing model. Let's explore the key benefits of edge computing. First, reduce latency. Processing data closer to the source minimizes round-trip times, enabling real-time applications and faster response times. Second, bandwidth efficiency. Local data processing reduces the volume of data sent to the cloud, saving bandwidth and reducing network congestion. Third, enhanced security. Sensitive data can be processed locally, reducing exposure during transmission and enabling better compliance with data regulations. Fourth, improved reliability. Edge systems can continue to function during network outages, providing resilience and continuous operation for critical applications. Fifth, cost optimization. Reduce cloud data transfer and storage costs, along with more efficient use of network resources and infrastructure. Finally, energy efficiency. Lower power consumption for data transmission, enabling more sustainable Internet of Things deployments and extended battery life for devices. Now let's examine the architecture of edge computing. Edge computing architecture creates a distributed network that processes data closer to its source, reducing the need for data to travel to centralized cloud servers. The key components include end devices, such as Internet of Things sensors and smartphones, edge nodes like gateways and micro data centers, the edge network using 5G, Wi-Fi or local area network, and a cloud backend for non-time critical tasks. This layered approach ensures efficient data processing and real-time responses. Let's compare edge computing with cloud computing. In terms of latency, edge computing offers milliseconds latency due to proximity to data sources, whereas cloud computing has higher latency, often over 100 milliseconds due to distance from data sources. Regarding location, edge computing is distributed across multiple locations close to end devices, while cloud computing is centralized in large data centers. For connectivity, edge computing can operate with intermittent network connectivity, whereas cloud computing requires constant, reliable network connectivity. Lastly, in terms of storage and processing, edge computing has limited resources optimized for specific workloads, while cloud computing has virtually unlimited resources with high scalability. Let's explore some real-world use cases for edge computing. First, autonomous vehicles. It provides real-time processing of sensor data for immediate decision-making, reducing latency for safety-critical operations, such as Tesla's onboard computer processing camera feeds for autopilot functions. Second, industrial Internet of Things. It helps in monitoring equipment performance and enabling predictive maintenance with minimal latency for manufacturing systems, an example being GE's Predix platform. Third, healthcare. It helps in processing patient monitoring data locally for immediate alerts and interventions, especially in remote care scenarios, such as wearable devices that monitor vital signs and detect emergencies. Fourth, gaming and augmented reality or virtual reality. It reduces latency for immersive experiences by processing graphics and game logic closer to users. For example, Microsoft's Xbox Cloud Gaming uses edge servers for game streaming. Fifth, smart cities. It enables processing data from traffic sensors, surveillance cameras, and environmental monitors for real-time urban management, such as Barcelona's smart traffic management system. Finally, mobile applications, where it offloads compute-intensive tasks from mobile devices to nearby edge servers, extending battery life and capabilities. For instance, Google's Live Transcribe uses edge computing for real-time speech recognition. How do we actually implement edge computing? Edge computing implementation requires specialized software frameworks that can efficiently distribute processing across edge nodes while managing resources effectively. Here's an example of edge node configuration using Amazon Web Services, AWS Greengrass. Now let's look at the implementation steps. First, identify edge requirements. Determine latency needs, processing requirements, and data locality constraints for your application. Second, select edge infrastructure. Choose appropriate hardware, like gateways or micro data centers, and connectivity options based on your requirements. Third, deploy edge software. Implement edge computing platforms like AWS Greengrass, Azure Internet of Things Edge, or open source options like KubeEdge. Fourth, develop edge applications. Create containerized applications optimized for edge deployment with efficient resource usage. Finally, implement security measures. Secure edge nodes with encryption, authentication, and regular security updates to protect distributed data. Edge computing comes with its own set of challenges. First, security vulnerabilities. Distributed edge nodes create a larger attack surface with physical access risks and varied security standards. A solution is to implement zero-trust architecture, encryption, and regular security audits. Second, resource constraints. Edge devices often have limited processing power, memory, and storage compared to cloud infrastructure. The solution is to optimize applications for edge deployment with efficient resource usage. Third, data synchronization. Maintaining consistency between edge nodes and cloud systems can be difficult, especially with intermittent connectivity. Implement robust data synchronization protocols with conflict resolution. Fourth, management complexity. Deploying, monitoring, and maintaining software across numerous distributed edge nodes can be a challenge. Use centralized management platforms with automated deployment tools. Fifth, standardization issues. There is a lack of unified standards for edge computing architectures, interfaces, and protocols. Adopt open standards and frameworks like EdgeX Foundry or Open Horizon. Finally, cost considerations. The initial investment in edge infrastructure and ongoing maintenance can be significant. Perform return on investment or ROI analysis, comparing edge versus cloud costs for specific use cases. Several key technologies enable effective edge computing implementations, providing the infrastructure and tools needed for distributed processing. 1. Edge artificial intelligence or AI machine learning models optimized to run on resource-constrained edge devices for local inference. 2. Containerization lightweight containers like Docker or K3s, enabling consistent deployment across heterogeneous edge devices. 3. 5G networks, ultra-low latency connectivity enabling more powerful edge computing applications and services. 4. Edge platforms such as Amazon Web Services or AWS Greengrass, Azure Internet of Things Edge, and Google Cloud Internet of Things providing managed edge computing services. Looking ahead, some future trends include 1. Edge cloud continuum, seamless integration between edge and cloud resources, creating a unified computing fabric with workloads dynamically placed based on requirements. This enables more flexible application architectures and resource optimization. 2. Edge AI acceleration, specialized hardware for AI inference at the edge, enabling more complex models to run locally with lower power consumption. This enables advanced computer vision, natural language processing, and predictive analytics at the edge. 3. Federated learning, training machine learning models across distributed edge devices without centralizing data, preserving privacy while improving model performance. This addresses data privacy concerns while enabling collaborative intelligence. To summarize, edge computing transforms how we process information and enables new applications by bringing computation closer to data sources. Core benefits include dramatically reduced latency for time-sensitive applications, optimized bandwidth usage and reduced data transmission costs, enhanced data privacy and security through local processing, and improved reliability with continued operation during connectivity issues. When implementing edge computing, balance workload distribution between edge and cloud based on requirements. Adopt containerization for consistent deployment across edge devices. Implement comprehensive security measures for distributed infrastructure. And plan for scalability and management of numerous edge nodes. For further learning, explore resources like the book Edge Computing, Models, Technologies and Applications, the Linux Foundation's LF Edge Project, the Edge Computing Consortium or ECC, AWS Edge Computing Certification, Microsoft Azure Internet of Things Edge Documentation, and the EdgeX Foundry Open Source Framework. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.